All right, so ozone. Ozone is formed in the upper atmosphere in the stratosphere. So it's above the troposphere. It's one of the few things that actually happens that makes a difference to us outside of the troposphere. As you remember, we talked about the layers of the atmosphere, and about 95% of all the gas in the atmosphere is in the troposphere. The effects, by the way, of global warming are in the troposphere. That's where it primarily happens. Weather all happens in the troposphere. So the stratosphere's only claim to fame in this case is the fact that the ozone layer forms here. And you have a reaction. You have the normal, stable form of oxygen gas, O2. They like to pair up, share their outer electrons. You probably, hopefully, remember from chemistry that many of these molecules are diatomic. And it's a stable form for them. But in the upper atmosphere, ultraviolet radiation has the property that it likes to break chemical bonds. Okay, it's what they call oxidizing radiation. It's one of the reasons why we don't want it down here at our level. But up there, where it's unshielded, it will cause these pairs of molecules to briefly break apart. Now, a lot of them are going to go back to O2. That's the way they're most happy. But some of them will regroup together as O3 temporarily. And in so doing, they're going to absorb a lot of that ultraviolet radiation. And then another property of it is the fact that O3 molecules, ozone molecules, absorb ultraviolet radiation before re-emitting it, and therefore take the energy off of it and reduce the length of the wavelength, make it less energy, and less with the actual ultraviolet wavelengths will make it to the Earth. About 95% are blocked out by this process. So that's a good thing, of course. That's the natural way of things. So we always look at the way the nature is and everything and the function it serves life, and that's obvious that that's filtering out that UV radiation is a very good thing for life here on Earth, life on the surface of the Earth, of course. So how do we mess this up? Bullet 4. Humans have produced these substances called chlorofluorocarbons, and we'll talk a little bit on the next slide about why we did and use such things. But suffice it to say, it is a completely artificial molecule. You do not find this in nature in any great quantities, or there's no process that naturally makes this happen. Most of your chlorine and fluorine are already bound up with metals. So it's not something that would normally happen. It was manufactured starting in the 1930s, and it serves a lot of purposes as it is. But one of the things that it does is that when these substances get into the upper atmosphere, that same UV radiation that catalyzes this reaction now will act upon this chlorofluorocarbon, that chlorine stands for chlorine, and break one of those chlorine atoms off. Okay? And there are a few things more radical than a single chlorine atom. So that chlorine atom is going to immediately go and grab onto an oxygen atom and break off one of those oxygens, and an ozone molecule, break off one of those oxygens that forms ClO, chlorine oxide. And from there, that particular molecule is also pretty reactive. Not as much as the chlorine atom, but it's a reactive molecule. This is what you have actually when you dissolve bleach and chlorine in water to make bleach. So that chloroxide atom or molecule will go on and react with the free oxygen atom from these processes above and form your O2 molecule there. It's stable. That's part of what drives it, is that formation. And that then, of course, will release that chlorine atom. Okay? And that chlorine atom then can go right back here to where it started, and the whole, there it is, right there. The whole thing can get started again. All right. So you guys got that all memorized, right? Very simple process, no big deal. Just boom, 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 that's it. No big deal. Now, it's a lot, so I want you to understand the most important things to know about this. Okay. First of all, what a CFC is, the elements that are on that CFC molecule, carbon, fluorine, and chlorine. And most importantly, that chlorine atom that's on there is broken off by UV radiation. And then that chlorine atom can go through and disrupt the formation of ozone. And it can continue to do that through a series of processes. It gets recycled, it becomes a free chlorine atom again, and can continue to break down ozone after ozone after ozone molecule. The estimate has been that one CFC molecule can break down about 100,000 ozone molecules. Okay, so that's a big part of the problem. You don't have to put a whole lot of this in the atmosphere to make a big difference. All right, so that's the reaction there. That's how people mess things up. Took us a little while to figure out this would happen. One of the things was that the people have known about this ozone shielding for over a century, and there's ways of telling how much of that ozone is in the upper atmosphere through satellite imagery and stuff, and also other observations from the ground, because we've got data going back before the 1950s, and what we've seen that it has decreased. They started noticing that it was decreasing. And it got to the point in around 2000 where it was about 50% of what it was in the 1950s. So that's a radical reduction. Okay. So we'll look at the next stage about what we did about that. So that's a call to a wake-up call, so to speak. This does occur, by the way, in the stratosphere, as mentioned. So we can get rid of this answer here. Otherwise, the other things that are in there are correct, except that's not how you spell fluoro. Thank you. Eraser. Fluorocarbon, F-L-U-R. Fluoro, carbon, okay. Fluorocarbon.
Oh,
you get the picture, okay? You can look it up if you want to have the correct spelling, but anyway, so that's where this ozone depletion occurs. The stratosphere is where it is, and the layers in that have decreased. One of the things you'll hear a lot about, and they ask about it on the national exam, so we should give it due consideration, is the ozone hole. The ozone hole is simply actually what happens naturally with the ozone layer over the poles, and what the effects of these CFCs have had on, to the point where the ozone naturally thins out around the polar regions, particularly the South Pole, because of polar vortexes and wind patterns and stuff like that. And then when you combine that with the CFCs, the action of these CFCs and other ozone depleting chemicals, then you end up where they've actually documented a hole, a complete window through that layer of the ozone layer, so that 100% UV radiation can get through. That may seem a little frightening, and it would be if it were any place other than the South Pole. So at the South Pole, fortunately, that's where it's occurring. I'm not sure exactly why it doesn't occur at the North Pole. Maybe Santa has an ozone generator he keeps cranked up so he can continue to work all year round. But at the South Pole is where they have documented and noticed it. And fortunately, of course, at the poles, you're not getting the energy from the sun is at its least, because it's going basically directly over it. The angle of incidence, as they call it, is very great, so it's not hitting right off like a perpendicular like it is at the equator. Second thing is, there's not a whole lot living down there, particularly that time of year. About the only thing that it really directly at the South Pole lives is there's a period where the penguins are there with their eggs. But that's during the winter, and this is actually their spring right here. This is our fall, early fall, or late summer, early fall, and their spring, early summer down there. So that is over Antarctica. Put that in there, and that is what's known as the ozone hole. The reason why I kind of dismiss this a little bit is because, like I said, in that position and everything, it does have a huge effect on that. And I think it's kind of for sensationalism that people say, there's a hole in the ozone layer, watch out. Well, if that hole was actually over, like a city or something, or over the equator for sure, you would see extensive damage to crops. I would assume that you would go outside and literally start to bake within minutes if there was an actual because it normally blocks about 95% of UV radiation. So it would be pretty nasty at those latitudes. Any questions? No? Alrighty. Alright, so what is so great about these CFCs? Why did we decide around mid-1930s to just start pumping out en masse into the atmosphere? Well, Freon, or CFC, is the most common brand name, CFC, that was produced. That was DuPont Company's claim to fame, made them multinational, multi-billion-dollar company. And it is basically a non-flammable, non-toxic, compressible gas. Now, all gases are compressible, but this, when you want a compressible gas for industrial applications, you want something that you can pretty easily liquefy. If you compress a gas, eventually, compress it and cool it, one or both at the same time, the molecules will get closer together and it will become a liquid. It'll take up much less space. But one of the main things that this is utilized for is a process called refrigeration. And it is what it sounds like. The refrigeration process has been around since before the beginning of the 20th century. But in the past, they've had to use other types of compressible gases, all of which were either flammable or toxic. Okay? So CFCs do a really good job at this. And like I said, they're both non-flammable and non-toxic, so that makes them, that made it able for people to have these types of refrigerating devices inside their homes, as in refrigerators, and then after that, air conditioning systems. So I'm going to try to briefly explain to you how your AC system works. Not that it's that important to the topic, but I think it's important. It's a good thing to know, and so we're going to look at it real quickly here, how that works. Basically, inside your house, if you have a central heat and air system, you have you've got a fan that's gonna blow air through the house, and over that fan, you will have it's like a radiator. It's a system of pipes. It's a metal box that has pipes in it. If anybody knows what a radiator is, you know what I'm talking about. One, you have one in your car. It's actually, you have a similar one right there on the back of that refrigerator if you want to look at what it looks like. So it's got tubes, it's got fins on it, and its purpose is in this case, it's called an evaporator. And what happens is you have a substance. And this was, in the past, it was Freon, not too distant past, as a matter of fact, because we have our downstairs air conditioning units, which we've had since we built our house in 2000, has Freon in it. We have an upstairs unit that we replaced about 5 years ago in it. It has an alternative, it has something called Puron in it, which does not deplete the ozone layer. So anyway, you've got Freon that comes into the house here. And when it's blue, it's a liquid. It's they compress the gas, so it becomes a liquid. So it's a liquid here. And then in this little evaporator thing, there's a valve that lets it open a little bit, so it's not under pressure anymore. When it's in this hose here, it's under pressure, high pressure. When you release the pressure on a gas that's been compressed in the liquid, it's going to go back into being a gas. Now, when that happens, it's evaporating basically. When a liquid evaporates, it absorbs heat from its surroundings. So if you absorb heat from the air around that something is in, what's going to happen to the temperature of that air? It's going to get hotter or colder? Yeah. It's going to get colder. You're going to take the heat out of it. Okay? So this heat basically gets absorbed by the evaporating Freon that's inside, and that Freon becomes a gas. So it leaves there as a gas. So we'll say Freon here is a liquid, and Freon here is a gas. Okay. Now that's going to go outside of your house, and you may notice these outside of your house. There will be a box. Big metal box with a fan in it. Anybody know what I'm talking about? You see that outside your house? It's like big, about this size, maybe smaller, and it's got a big fan in it. There'll be fans, there'll be air blowing out. You probably haven't looked around. If your house has central heat and air, then you'll have one of these things in there. So anyway, when it goes out there, the purpose of this one is basically to cool off that Freon. So this has got a big cooling part to it inside, okay, and to cool it off some. So we'll represent that by little spaces here and there, okay. And then it goes from there into a compressor, which, as its name implies, compresses that liquid, that gas back into a liquid, which then can go back inside and do the whole process all over again. So basically, this is displacing. This fan is blowing the heat from that hot Freon off, so that displaces the heat outside. You got the heat going inside to the Freon. Freon goes outside. The air blows across and blows that heat out into the atmosphere, and that's how your air conditioning system works and cools your house off. Okay.
So how does the Freon get out?
In the atmosphere?
Yeah.
Just and this is a good question, Jess. How does the Freon get out in the atmosphere? With home units, they did home systems last. Okay. So, because it doesn't get out that much, but you'll ask your parents, you ever had to have a recharge on your Freon, whatever, there's, every system like this is going to have some tiny little leaks. Sometimes they'll be major, and your AC will be out in minutes as it escapes in the atmosphere. Sometimes they'll be very small, and it'll leak out, and the pressure will get lower and lower over time, but of course that Freon is leaking out into the atmosphere. One of the applications, if you remembered on the slide before, was as an aerosol, which is what you have in spray cans. You have compressed gases in the spray can. That's one of the reasons why you don't see those metal type spray type cans as much anymore, because it's hard to come up with good substitutes for for that. So a lot of times you pump bottles and stuff. So that was directly in the atmosphere. So when they figured out something was wrong, they convened to do the Montreal and Copenhagen protocols. They had two of them. This was in the early 70s. And say, look, this is a problem. This is going to be very serious. We need to stop putting these substances into the atmosphere. Okay, so they phased it first out of aerosols, 1970s. Freon was phased out of aerosols, and then through the 90s. In the 90s, they started phasing it out of automobiles. Okay, and like I said, now for the past 10, 15 years, anything I think you've gotten in about probably the past 10 years, home air conditioning systems, stationary units, big refrigerators and stuff. Then they have those are going to be replaced with an alternative. Puron is a brand name and stuff like that. What they do is they replace the chlorine on them with hydrogen atoms, and they work just as good. So that was one of the reasons why this has been very successful, because of the fact there's a cheap alternative. It's not too much heartache in doing it. It's not anything like trying to control your carbon dioxide emissions. That's much more difficult and much more broad over all industries. This is a small segment. So these protocols, they got together and they said, let's stop producing these substances. CFCs were the main ones. I also want to point out there's other ODCs, ozone depleting chemicals, such as methyl bromide, because bromine, is very similar to chlorine, and the bromine will do the same thing to ozone molecules in the atmosphere when these get up here. This is used as an insecticide. It's what they call soil fumigant. It's a gas, and they pump it into the soil. It kills all the bugs and everything in there. And also something called halon, which is a very inert gas that they've used in fire extinguishers before. So the halon, not a huge amount of that having been put in the atmosphere, and they phased that out of fire extinguishers and stuff since then. But those are, of course, the main culprits are CFCs, chlorofluorocarbons. And so consequently, they've done that, and it's been effective. The ozone levels are starting to rebound. Now the problem is that those CFCs and everything else has been put out in the past. They last for 25 to 40 years in the environment, and so consequently, they're still having some action, but they've really started to see a turnaround and a thickening of the ozone layer. So maybe 10, 15 years from now, you can go from SPF 50 to SPF 25 or something like that. But there has been a positive effect. Now, I kind of jumped ahead. We got to the cures, and in fact, we didn't really talk about the effects of ozone depletion on the environment and on people. And the effects are more UV radiation. So whatever effects more UV radiation would have, okay, put your phone away, would be the main things that are damaged from this are plants. Because plants are designed to absorb sunlight but this is an overload. So that chlorophyll is trying to get sunlight and everything. When it's hit with that UV radiation, just blows it apart. Literally oxidizes it, shoots the electrons off it. Like I said, if you want to see this in action, take an indoor plant that's supposed to be indoors all the time and put it out in the noon sun. See what happens to it. Hopefully it won't be a favorite one because it'll kill it. That's one of the things. And then, of course, when you have single-celled organisms that are plants, and that's primarily plankton, that's about all of them. You don't have single-celled plants like on the ground so much. A little bit, some, but most of your plankton in the ocean, then they're particularly going to suffer because it doesn't mean just that they'll be less productive. They will, it's going to kill them. Okay, so that's a big concern. Not only the basis of the food chain, but that's the #1 supplier of oxygen in the world is phytoplankton. Group 5, I'm going to give you, like I said, you go for the ace in the hole biodiversity, pretty much have an environmental effect. You can always expect lack in biodiversity. So that's good. I'll give you the credit for that. But more specifically, what happens, which leads to this biodiversity, is a decrease in productivity. Who are the producers in an ecosystem? Producers. What are producers? What's an example of a producer? Plants. Plants are your producers. They use photosynthesis. Producers, productivity. Productivity is an ecological term, means simply how much photosynthesis is going on in that ecosystem. That's it. They count how much chlorophyll is there and everything, how much sunlight it gets. That's how you can actually calculate productivity. This UV radiation damages that process, damages chlorophyll, productivity decreases. Okay, so that's environmental effects. Human effects, of course, skin cancer, you're well aware of that, hopefully. Cataracts also are an effect from exposure to UV radiation, and yes, people with lighter colored eyes, you are more at risk for developing cataracts. And then, of course, one last thing as far as human impact, and this is kind of one of those gimme things, this is what you're always going to see. If you have something that damages plants in general, then of course it's going to damage food crops. And I'll take edible for that because of course food crops are edible. But it's going to damage food crops. Okay? And therefore affect human health. So now for us that might mean potatoes, tomatoes, whatever kind of produce is more expensive. But for many people around the world, that means there are going to be more malnutrition and more people starving to death. So there you have it. Any questions? Seniors may go.